Alright, day 2 of FRQs. So technically you should be spending 15 minutes on, this will be Tuesday. I don't know what that makes it date wise. I think it makes it March 31st or April 1st. I think it's March 31st, it's Tuesday anyway. There's 2 short ones here that you should be doing today. So number 4 should be a 7-minute question. We skipped 2 and 3 in 2014 because one of them is a buffer problem and one of them is a electrochem problem, and at this point we figure out that AP exam's not even going to ask about those 2. So not only have we not covered them, but they're not going to ask about them, and so we're in good shape there. So this is a quick little kind of equilibrium problem, and so off and running. Here it comes. It says when heated, calcium carbonate decomposes according to the equation above. They don't need to give us that equation. If they give us calcium carbonate there, we should already know what the products are going to be. Metal carbonates, always breaking in metal oxides and carbon dioxide. So we should feel comfortable with the equation. It's balanced already, which is nice. 50 grams of the calcium carbonate goes into that vacuumed out 1 liter rigid container, and then it's heated to a temperature of 1100 Kelvin. As the container is heated, the total pressure of carbon dioxide was measured over time. And at this point, all of you should be thinking, I've got a volume, I've got a temperature, they're talking about pressure, and so this screams ideal gas law. I don't know what the format of the exam is going to look like at this point for you guys, because they're going to shorten it, but I would still bank on ideal gas somewhere along the way. And so here we go. So they give us a little graph. It looks like this. It talks about pressure over time, and we can see initially we have no pressure because we have no gases in the container, just the calcium carbonate. As it's heated and decomposes, the only gas that we have to play with is this carbon dioxide gas, and so that's the only thing that's going to be contributing pressure here, which is good for us. So here we go. Number 4a says calculate the number of moles of carbon dioxide present in the container after 20 minutes of heating. So if we're talking about pressure and we've got a temperature and we've got a volume, I am going for ideal gas law here. We have the pressure at 20 minutes from the chart. Not only that, but we have the pressure here because they gave it to us as 1.04 atmospheres. So here we go, PV equals nRT. This is number 4. PV equals nRT. They gave us a pressure. The pressure here was 1.04 atmospheres times the volume. We know it just happens to be a 1 liter container because they are sweet angels. You'll notice they give us 3 sig figs on that volume. The 1 liter container. Number of moles is what we're looking for. This question asks for moles of carbon dioxide present. So moles, this is a gas law, so we are 0.0821 liters times atmospheres over moles times Kelvin times the temperature this thing reaches is 1100 Kelvin. And we plug this guy in and we solve for the number of moles of carbon dioxide gas. And when you plug that in, you get 0.0115 moles of CO2. 3 sig figs here in the number of moles. That's part A. Calculate the number of moles present after 20 minutes. Part B says the student claimed that the final pressure in the container in each experiment became constant because all of the calcium carbonate had decomposed. Based on the data in the experiments, do you agree with this claim and explain it? And so when we look back up at the top of this, it used 50 grams in the experimental data, and then it says the student repeated, but this time used 100 grams of calcium carbonate in the experiment, and the final pressure was exactly the same, the 1.04, and so the pressure didn't change. And because of that, because the pressure didn't change, it means that the same amount of calcium carbonate decomposed, and so there's no way that this thing all the calcium carbonate decomposed, because if all of it decomposed, we would have twice as many grams of calcium carbonate decomposing, and we would have much more carbon dioxide produced as a result. So the answer is no. The answer is no. Because the same number of moles of CO2 were produced. If the pressure is the same, we've talked about this a ton, if the pressure is the same, and it was at the end of this, then that means the number of moles of carbon dioxide produced were the same as well, because those are proportional to each other, the moles and the pressure. Then we get to part C. Part C says after 20 minutes, some carbon dioxide was injected in the container, initially raising the pressure to 1.5 atmospheres, with the final pressure in the container be less than, greater than, or equal to 1.04. Explain your reasoning. This becomes a equilibrium question. If we add a bunch of initial pressure, we have to figure out which way is this equilibrium gonna shift. And because there's no temperature change, so we initially have more pressure of carbon dioxide, because there's no temperature change, and our Kp only includes the carbon dioxide, products over reactants, but the other two pieces of the equation are solids. So that Kp is going to equal the pressure of that CO2, and because there's no temperature change, the Kp doesn't change, and because there's no equilibrium constant change, that means the pressure of the carbon dioxide would be the same. So the pressure of CO2 would remain the same because I got to get better at getting my paper under the camera, because the temperature is constant. And then I would write the equilibrium expression there that way. And that kind of answers question D for us when we look at this one, because question D says, are there sufficient data obtained in the experiments to determine the value of the equilibrium constant, the Kp value, for the decomposition of CaCO3? It says justify your answer. Your answer is yes. The Kp would equal the pressure of the carbon dioxide, and that's it. Products over reactants, there are no other products or reactants to deal with, and so not only is it true that we can find the value, I wrote down the value as 1.04 for the Kp, and so I would justify it that way. It's not really a calculation, but it is justification for it to show that equilibrium expression. So that's number 4. Should be a quick hitter. Should be 7 minutes. When there's 4 parts to this, these are only 4-point questions, at least in the old format of the exam. And so if there's 4 pieces, every one of those pieces would be worth 1 point to you. If you have any questions on it, make sure you email me or write something in comments on the post for me, and I'll double check and make sure we get clarity. Thanks. We'll talk to you later. Bye.